unfortunately the much more technical than either of the previous two talks, and in fact it's something far outside my area, and so I'll only discuss the very impressionistic outlines of how the proofs look like. So I myself don't know the details. I haven't read through the details of these proofs. Anyway, so yesterday we discussed spectral decomposition of L2 of G of A over G of Q that had contribution from various standard parabolics. Okay, so I did not. Maybe I should have put a slide recalling various notation, but I guess so. We had the spectral the L2 of G of A over G of Q was made of contributions from standard parabolics P. Okay, so the P's that we are going to see are standard parabolics, and then we had this I AP star. What did that look like in the upper half plane picture? They were the IR. Okay, so from I AP star, we had to look at functions into some particular space. Okay, sorry, I should have written MP here instead of M. Okay, so this was actually MP, or you can take that M is the standard degree of P. Okay. So first of all, you have to look at the discrete spectrum of the Levy. To get the continuous spectrum of G, you have to look at the discrete spectrum of the Levies. Then you have to parabolically induce from the Levy or the parabolic to G of A. And then what do? You have to kind of integrate it over I AP star. Okay. For that, you have to look at measurable square integrable functions from I AP star to this Hilbert space. Okay, this is a Hilbert space. And then for these, we defined a map into L2 of G of A over G of P, and that map took like theta P comma phi. So this is this phi of G is, so two elements in this space. So these are like automorphic sums on the space G of A mod N of A M of Q. From there, you have to do the Eisenstein construction. Okay, so in the upper half plane picture, this was exactly like the E of Z comma S. Okay, so the G was like the Z in the upper Z in the upper half plane, and lambda was like the S on IR, and then you have to integrate. Okay, however, this was not all that was there. The contributions from various parabolic subgroups were so to speak intertwined using intertwining operators. Okay. So, what is the spectral decomposition? What was the form of the spectral decomposition? For each standard parabolic P, you had to take a phi P in place of this phi. Okay, so phi P's, and then they had to map to summation over P, NP inverse theta P phi, and not just that, the phi P's had to be related to each other according to the intertwining operators. Okay, so it was not an arbitrary collection of phi P's, but they had to be mediated between each other by the intertwining operators. Okay. So that was the theorem that I stated at the last time. Okay. So the first thing I want to discuss is, why is this map an isometry? Okay. So sorry.
What was NP?
So NP was the number of parabolics which had the NP as a Levy subgroup. Yeah. But we are not going to use that in any way. So okay. So you see, it would have been nice if we did not have to worry about intertwining operators. Okay. In an idealistic picture, you could think that every standard parabolic contributes a chunk of L2, and that was by this as an isometry. Okay, that's unfortunately not true. If that were true, how would the theorem look like? Okay, so if that were true, the theorem would take the following fashion. So I'm going to write the wrong expression, which I will correct on the slide. So theta P phi, comma theta P prime phi prime is going to be as follows. It would have been, you see, you want that to be an isometry, right? So it would basically take the form integral I AP star. You are integrating that Hilbert space which was written upstairs. So it would have taken the form integral I AP star phi P of lambda, phi P prime of lambda prime, phi P prime of this is not the case. If P not equal to P prime, this would have been 0. This would have been 0. If P equal to P prime, then it would have been integral phi P of lambda, phi P prime of lambda, d lambda. Okay. This was exactly what we did with the toy case of K cross A, the compact group cross vector space that we discussed yesterday. But this is not quite true because the contributions of P and P prime are intertwined. So what do you have to actually do? You have to do summation W element of all the Y group elements that can intertwine the contributions of P and P prime. So namely I am writing that as W of P comma P prime. And then what you should do is integral over I A P star. See, the problem is phi P of lambda is associated to some object associated to P. Phi P prime of lambda prime is associated to P prime. So you have to actually apply the intertwining operator. Yesterday I wrote this by M of W comma lambda. So you have to apply the intertwining operator to go from that space induction P of A to G of A to the corresponding space induction P prime of A to G prime of A, and then pair it with Phi P prime of lambda. And the pairing will take place in the space associated to P prime, and then it will be a D lambda. Okay. So that is what we would get given that you have to intertwine these contributions. Okay. So I have just written that over there. Integral over I A P star. You apply what we denoted, whatever intertwined the contributions of P and P prime, apply to Phi of lambda. Pair it with Phi prime of W lambda. Okay. This had to be W lambda because only W lambda is W lambda is what W takes lambda to. Okay. So this is the statement. This is basically equivalent to the statement that the map in the spectral decomposition that I discussed yesterday was an isometry. Okay. So this is the main statement, and this is of course due to Langlands, but Lapid gave a shorter proof. Okay. Now, of course, I am not going to discuss a proof of this, but I'll discuss some ideas of what all go into Lapid's proof. Okay. Yeah.
Use the reduction to the customer case
yeah, so the thing is, Langlands proof involves a contour integral, right? So he starts with pseudo existent series, and then he shifts, and then
okay.
But Lapid's proof, is a completely different thing. Yeah, I'm going to. Yeah, so that's what. Yeah. So you see, so think of this as a summation of Eisenstein series. Okay. So this is an integral of Eisenstein series, but let's just pretend that this is a summation of Eisenstein series. So you have something between something involving an Eisenstein series here. You have something involving an Eisenstein series here, and you have to take the dot product. Okay. You might like to take the integral inside, and then sorry. That's the final answer. But so this is like a summation of an Eisenstein series. So if you want to pair this guy with another guy of the same form, you might want to pair the integrand here with the analogous integrand for P prime. Okay, and then you might want to kind of take the integral inside or something. But that's of course impossible because Eisenstein series are never in L2. Okay, so what should you do? You have to actually replace Eisenstein series by something truncated, some truncated version of Eisenstein series, and you need a formula for the inner product of truncated Eisenstein series. Okay, so that is what we're going to do. Okay, so the difficulty is that this series doesn't converge, so you cannot naively prove that this sort of thing is an isometry. So the key result that is going to be proved is you take the Eisenstein series, truncate both of them, and then take their inner product. Okay. So this time you are not integrating over lambda, you have fixed a lambda. Okay. So what is this truncation? I will come to the truncation later. Oh, this is. But roughly speaking, let me give you an idea of what lambda t does. Okay. Again, go back to the upper half plane picture. Okay. In the upper half plane, you have a fundamental domain of this shape that Professor Ravi Raghunathan discussed earlier today. So here you can choose a cut of t.
Sorry.
Yeah, sorry.
You never said what nice means to file.
So nice means that it has to be CC infinity,
CC infinity.
and it has to take values in a finite dimensional subspace of the target. Okay. But those are enough to be dense in here. Okay. So I'll describe what truncation does within a fundamental domain. Okay. So as long as the y coordinate is less than t, you are keeping your same automorphic form f. which is the Eisenstein series in this case. Above T, you are subtracting from F its constant term. Okay. So if you subtract constant term of F from F, you are basically forcing it to rapidly decrease. So similarly here, you have done this operation called lambda T to force this Eisenstein series to rapidly decrease. Okay. So this theorem will essentially follow if you prove this theorem. So now let me state how this expression has to look like. Okay. So how should this expression look like? Truncation involves constant terms, so you are basically you can taking a constant terms with respect to various parabolics. So the answer is actually going to involve a sum over various parabolics q, standard parabolics q. But then these are Eisenstein series respectively associated to p and p prime. So you have to look at all the ways in which you can associate p with q, and also all the ways in which you can associate p prime with q. Okay. So that's how the formula is going to start. The formula may look intimidating, but it is actually a very reasonable thing. I'll explain verbally how it is going to look like. Okay. So as I say, lambda T of this inner product is going to be summation over standard parabolics q. You look at all ways of associating p and p prime with q, and it's only going to hold for T deep enough in a certain cone, which is the same as saying that when you take inner product on the upper half plane, you are estimating inner product of Eisenstein series only above only if you truncate it above a particular T. Okay. So for T deep enough in a certain cone, what is going to happen? The main term in the summation is going to be as follows. You have to transport your phi. You see, phi was in the space associated, induced space AP associated to P, and this was an automorphic form in AP prime. So you have to transport using intertwiners from P to Q and also from P prime to Q. Okay, and then take inner product in the L2 space associated to Q. That is the induced space associated to Q. So this is exactly like you expect this to kind of reflect the inner product structure on the inducing Hilbert spaces. That's sort of what is happening here. And secondly, another remark is that we are not exactly getting an exact formula for the inner product of truncated Eisenstein series. One is only getting it up to an error term. Okay. Then there is one more factor, and that factor is a product of a volume and something that depends on T, because after all you would expect T to not really show up here. Okay. We don't need to bother about what this is, but basically truncation involves various convex regions in various vector spaces, and this is like a Fourier transform of such a thing. Okay, so that's not. So this is the theorem. So Arthur actually proved it using spectral decomposition. Okay. Before that, if phi and phi prime were cuspidal, that is, if you started with cusp forms on your levies, then this inner product formula is actually originally due to Langlands. In that case, the inner product formula is exact. Okay, so there is no order of e raised to minus t. Various constant terms vanish for cusp forms. That's why in the cuspidal case this is much easier. Okay, so in that case it's due to Langlands, and there is an alternate proof by Jacquet, Lapid, Rogowski. The general case, Arthur used Langlands spectral decomposition to prove this. However, Lapid, unlike Arthur, avoids spectral decomposition, and instead he is using this to prove towards proving the spectral decomposition. Okay. So in fact, the previous slide was written assuming that Eisenstein series are holomorphic on the relevant imaginary axis. Okay, that was an important point. But Lapid actually does not assume it. So what he does is he replaces this theorem with a weaker but unconditional version. He uses this theorem to prove previous pages theorem, and once he gets previous pages theorem, he can actually go back and prove that Eisenstein series are actually holomorphic on the imaginary axis. Okay, so Bernstein and Lapid only prove the meromorphic continuation of the Eisenstein series. The fact that they are holomorphic on the imaginary axis is not proved by them, but then Lapid deduces it. Okay, so this is in Lapid's article in the Shahidi's 60th birthday conference. Okay, that's where you can find it. It's there on K Mathematical Institute web page.
Sorry, what is restrictive? Can you restrictive US mean meromorphic as opposed to?
No, so the thing is that, yeah, sorry. Yeah.
The question is, what is restrictive?
He's not proving this under restrictive assumptions. He's proving this statement under restrictive assumptions. Namely, he assumes that phi and phi prime are parts of some continuous family of parameters where the Eisenstein series are assumed to have nice properties. For that, he proves them. And then, yeah.
But he only uses the meromorphy of Eisenstein series in that family.
Yes, exactly.
Oh, he uses meromorphic.
Yeah. Lapid's proof assume meromorphy, but holomorphy in the imaginary X is a consequence of this property. Okay. Okay, so this was the definition of truncation, but since I am going really slow, I think I'll skip the definition of truncation. Basically, I described how truncation looks like in the upper half plane case. But then there is also an additional summation here which reflects the fact that I am not just truncating things in a fundamental domain, but in a the whole of upper half plane. Okay, so it's an alternating sum. But basically, just remember that you are subtracting various constant terms from f, which capture the asymptotics of f, so that when you subtract various asymptotic terms, you can turn automorphic forms into rapidly decreasing functions. Okay, that's the main thing to remember regarding truncation. Okay, so now we had to so there had to be a proof of inner product of Eisenstein series, and the key tool used by Jacquet, Lapid, Rogowski in the cuspidal case and by Lapid in the more general case is what is known as regularized inner product. Okay, so what does regularized inner product mean? Consider an expression like e raised to minus lambda x, x raised to s dx. Okay, such an expression will only be convergent for certain lambda. If lambda is negative, integral e raised to minus lambda x, x dx will be convergent. But whatever answer you are getting is actually holomorphic in lambda. Okay, therefore is actually meromorphic in lambda. Therefore you can actually meromorphically continue it and declare e raised to x into x raised to s dx to be something. Okay, so as the value of that meromorphic function at lambda equal to 1. Okay, so that is what is called regularized inner product. So you somehow realize a way to write your integral as part of a family. Your integral itself does not converge, but somewhere else in the family it is actually going to be a convergent integral, and by meromorphic function you are going to realize your integral, and such a thing is called a regularized integral, and in this case a regularized inner product. Okay, so what does Lapid or Jacquet, Lapid, Rogowski do? The inner product of truncated Eisenstein series, what they do is they write it as an expression involving regularized inner products of constants of that series. Okay. So originally the problem was that inner product of Eisenstein series does not exist. In fact, regularized inner product of Eisenstein series does exist, but that does not give you what you want. So you actually truncate it, but then to understand the truncated stuff, you actually go to the regularized stuff of various constant terms. Okay. So basically, it falls into a framework called regularized integrals. You truncate a function, but then evaluating the integral of the truncated function, though this is a convergent integral, its integral is a difficult thing. So you split into various pieces which may not themselves converge, but you can make sense of them using regularization. Yeah, sorry. Yeah.
This is not the same that Arthur's truncation truncates something and shows that there is a polynomial expression in T and then a constant term.
Yeah, so it is a polynomial expression in T. Yeah, so indeed Arthur does not use regularization, but somehow these regularized things are used by. So that's the approach of Jacquet, Lapid, Rogowski towards the computation. In fact, we can compute things without using regularized inner products, which is what Arthur did. And for upper half plane modulo gamma, you have the classical Maas-Selberg relations, which are the truncated inner product of truncated Eisenstein series, and Kesselman's earlier work has a formula for the inner products using regularization, which is exactly what Jacquet, Lapid, Rogowski also do. Okay, so yeah, so this is regularization is used as a computational tool here. Okay, so I'm just saying a bit more on regularized integrals because this is a completely elementary thing. So if you have any finite dimensional vector space V over R, you can consider certain functions which are called exponential polynomial functions. Okay, of this form. Okay, so product of an exponential function and a polynomial function, you can regularize their integrals over a nice cone in P. Okay, like e raised to minus x, e raised to lambda x into x raised to s dx. You integrate that from 0 to infinity. Okay, I didn't mean from minus infinity to infinity. Okay, what are these functions? These are very special functions. We are not integrating arbitrary functions. One property that these functions have is that these are precisely the functions on a vector space which are finite under translation. That is, if you look at all the translates of this function, their span is actually a finite dimensional vector space. Okay? So that's actually a very easy and interesting property to verify. So how do you integrate such a function? You are multiplying it by some function like e raised to omega comma b. If you do that, for omega, which actually is rapidly decreasing on your cone of interest, such an integral will converge and then you meromorphically continue in omega. Okay? So that's the philosophy of regularized integral. And here is the example that I described earlier. So why does this help? Maybe I will not describe details here, but basically what you will need to do is that you have an automorphic form, you have various constant terms of that function, okay, called fp. So please ignore whatever I have written here. To get regularized integrals of automorphic forms, what you need to do is you have various constant terms of your automorphic form, and you have to somehow make sense of their regularized integrals. And why does that help? The point is that the constant terms have what are known as exponents, which I am going to discuss, and there these polynomial exponential functions naturally show up. Okay, so let me give you an analogy. Okay, so you are on the upper half plane again. Remember, what is the constant term of the Eisenstein series? This took the form something like y raised to s plus half plus something times y raised to minus s plus half, right? From our perspective, this is actually an exponential function because y is like the a g comma infinity and it is the log of y that is associated to our vector spaces AP. Okay, so this is actually an exponential function, but presumably if you take more general automorphic forms, you will get y raised to something times some polynomial in log y. Okay, so this is related to what Professor Ravi Raghuvanshi said, namely automorphic forms on GL1 are basically exponential polynomial functions. Okay, so these functions are very related to automorphic forms, and to understand that relation, we need to move on to the notion of exponents. Okay, so I am going to discuss the notion of exponents in the next page. Okay, so suppose f is any automorphic form on G. So my slides are more or less, every slide is independent of the previous, okay, or most slides are independent of the previous page. Later that might not be the case, but right now it is. Okay, so our problem is as follows: f is an automorphic form and you have fixed a parabolic and you consider a constant term of f. Okay, yesterday I said that fp is a function on g of a over n of a m of q. Okay, so that's an analog of h mod n, and that is actually an automorphic form in the space that I denoted AP or G yesterday. Okay, and we also had this expression called a m comma infinity, which was the connected component of the maximal split torus in the center of M. Okay, the R points of connected component of the R points of the maximal split torus in the center of M. And I said that via the log map, it was isomorphic to a vector space. Okay, via a log map. So this guy, and I told you yesterday the following. So when you want to analyze functions on G of A modulo n of A m of q, what do you do? I said that Iwasawa decomposition gives you a homomorphism called HP into AP. Namely, you write an element here as n a m k, and then you look at log A. Okay, so that is what Iwasawa decomposition gives you. And I told you that this is the analog of log y. Okay. So everything depends on the a m comma infinity factor. So this a belongs to a m comma infinity. So we want to study how such a function changes when we multiply it by an element of a m comma infinity. Okay. So the point is that will lead to exponential polynomial functions. Okay. So recall that this was a vector space, and then okay. So and this is actually what is. Sorry, why is this? Yeah. So Sometime back I asked the question of what are the translation finite functions RT to C. Okay, and is there anything I should do or? Yeah, maybe this is better. So I don't know if it is capturing. Okay. Okay, so translation finite functions from RT to C are precisely the exponential polynomials. Okay, so this is a very statement about generalized eigen decomposition of R acting on any finite dimensional vector space. Okay, R is an abelian group, but it does not act completely reducibly. Okay, so R can, for instance, R can act just by a character e raised to lambda x, or R can also act by x goes to 1 and 0 1. Okay. So anyway, the consequence of this is as follows. Okay, so remember, given an automorphic form f, we want to study how this constant term fp is behaving with respect to the action of this group a m comma infinity, because this thing captures the analog of the height on the upper half plane. Okay, and the consequence is that you can always write the automorphic form fp as an exponential polynomial. Okay, so what is it going to look like? So I have written here only the exponential part. The polynomial part has been absorbed into these auxiliary expressions fp comma 0 comma lambda. Okay. So the point is that fp of g will be some exponential function which will only depend on the a m comma infinity coordinate, which is what we have denoted by hp of g, together with something where this fellow acts by a polynomial. Okay. So all that I have tried to convey in this slide is that if you have an automorphic form, its constant term along p will have an action of this a m comma infinity, and that action will be basically by some exponentials and some polynomials. Okay. Sorry.
So fp 0 lambda is a polynomial on the start, right?
No. So it's a function on g. Yeah. So I should have written of g or something like that.
Yeah, all that.
Yeah.
I mean, the dependence on lambda is polynomial.
Yeah, it has a dependence on lambda, which is polynomial.
So then the EP should act like a threshold.
Yeah, you're right. So no, what? No, I think it's a polynomial, right? It will be like y raised to s times log of y. Yeah. I mean, anyway, it is you are studying it as a function on AP, so the growth is polynomial, right? Yeah. Okay. So yeah. So roughly speaking, there is an exponential part to the growth and there is a polynomial part to the growth, and asymptotics is always determined by the exponential part. Okay. So that is what I wanted to say. And there is a issue of Rope shift here, which I'm going to ignore. Okay. And so, because Lapid is interested in inner product of truncated Eisenstein series, he uses the computation of constant terms of Eisenstein series, which I have just recorded here. Maybe we will not use it, but all I want to say is that it is some summation over some Weyl group elements, and the intertwining operators are going to come here. Okay? Maybe I will not on this later, but perhaps unlikely. Okay? So roughly speaking, the idea is this: you wanted to prove that something is an isometry, therefore, and that by some general analytical stuff, it came down to inner product of truncated Eisenstein series, and to compute the inner product of truncated Eisenstein series, you used as a computational device regularized inner product which involved Automorphic continuation, and that involved exponential polynomial functions, which were a natural thing to arise because constant terms of automorphic forms, their asymptotics can be described in a very nice way like this. Okay, so that is all that I want to say about Lapid's proof, I guess. So now I'll say something about the work of Delon. Okay, so this is all I wanted to say about why the map from this space that I denoted L onto L2 of G was an isometry. What Delon shows is he explains why this is actually surjective onto L2 of G. Okay, L2 of G of A over G of Q. Okay, so again it's going to be a very crude idea. So this is again going to be mostly independent of what I discussed in the Lapid's equation, though there will be some talk of exponents. So here, the statement itself does not involve automorphic forms. first we want to reduce it to some question involving automorphic forms, but you can't do an L2 pairing for arbitrary automorphic forms. Okay? Because inner product is not going to converge. Automorphic forms are not in L2. Okay? You can pair a slow growing automorphic form with a tempered automorphic form or something, but not otherwise. So first of all, we will be interested in, for each parabolic P, we will be interested in a subspace of what are known as square integrable automorphic forms. Okay? Which are defined by some sort of square integrability condition. So if P were equal to G, these would be just the L2 automorphic forms. But here P is not equal to G. Okay? There is another condition on central characters which makes this well defined. This space does not have an invariant integral, but the central character condition is that exactly whatever is needed to get the invariant G of n invariant thing comes out. Okay?
What was Maxcal?
Sorry?
What was Maxcal L?
So the entire spectral decomposition takes the form that some space is isomorphic to L2 of G. Right? For instance, for a vector space, it will be like L2 of I V star maps to L2 of V is an isometry. That's the statement of Fourier transform. So here, it is that space, it's the analogous space for G of A over G of Q that we had discussed, that we had taken to know. Yeah. So this is the isometry. We want to prove that this is an isometry. That's the main thing, right? This is a bijective isometry. Okay. So this is the space of square integrable automorphic forms. There is another way to describe this space, which involves exponents, but I am not going to go into the details because this is anyway an impressionistic sketch. Okay, then we'll also need the notion of tempered automorphic forms. There is a space called tempered automorphic forms A temp of G in A of G. Okay. One way to define it is there is a definition involving growth conditions, and it basically says that exponents, all exponents should be conducive to slow growth. Okay, I am not defining this precisely, but in the upper half plane, it says that the exponent should grow only like y raised to half. I mean, the automorphic form should only grow like y raised to half as y goes to infinity. Okay, because y raised to half into y raised to half by y square if you integrate, that just takes to b square integral. Okay, so this is what the space that truncate denotes as A log of G. Okay, so this is bigger than A2 of G. So they are not rapidly decreasing, but that are of slow growth. Okay, what does slow mean? The exponents do not contribute to any growth. Only the polynomials can create a growth. That's the meaning. Okay, of slow growth. There is also a different definition of tempered by Bernstein in a more general setting, and all that we are going to need is that tempered in Bernstein's sense implies tempered in the above sense used by Franke and Delon. Okay. So now remember, we want to reduce the question of subjectivity to a question involving automorphic forms, but L2 pairing does not make sense for arbitrary automorphic forms. Okay, so to reduce it to automorphic forms, we have some notion called wave packets. Okay, so it's actually a much simpler thing than the object that we saw yesterday. So yesterday, what was the, or even at the beginning of today's lecture, what was the object that we discussed today? We started by discussing integral over I AP star E of G comma phi of lambda d lambda. Okay, so phi was a function which took AP star to a complicated an induced space from an L2 space, right? So phi was a function which took I AP star to some complicated space. Here, the analogous thing is a much simpler thing. A is just a CC infinity function on I AP star. Okay, the phi here is actually a fixed fellow. It is not a function from I AP star to the induced space. It is just an element of that induced space. Okay. So it's a simpler thing that it's almost a special case of the thing that we saw earlier. Okay. So this is what is called the wave packet attached to a parabolic P, a phi in AP2 of G, and a CC infinity function. Okay. So this is thought of as a function of G. Okay, EP phi of A of G is equal to integral A of lambda E of G phi lambda d lambda. Okay. So it's not an Eisenstein series, but you are kind of modifying it by a CC infinity function. Okay. So one property that Delon proves is that this guy is always rapidly decreasing on G in an appropriate sense. Okay. So what is the advantage of having a rapidly decreasing function? You can always pair it with an element of a temp of g, because a temp of g means the growth is really slow. You can always pair it with something which is rapidly decreasing. Okay. So this is a step towards reducing a question about L2 to a question about automorphic forms. Okay. And then this is a lemma which doesn't take a lot of space but is kind of crucially used. If the image of the isometry were not the whole of L2 of G, Delorme shows that there is a non-trivial tempered form, non-zero tempered automorphic form psi with the property that it is orthogonal to all the wave packets. Okay, so this is the lemma that he has over here. Okay, this is not surprising. If you expect that something is not L2 of G, you expect to get something which is orthogonal to even things of this form, the more general things of this form that we had written down, certainly they should be orthogonal to wave packets. Yeah.
The closure of all the wave packets is the same as is the image of curly L.
Well, that's part of, that's kind of what we want to show. Oh no, it's kind of curly L. Yeah, it's kind of curly L. Sorry, yeah.
This is sort of saying that if something is outside curly L, then
Except that here one is taking psi to be tempered, one needs psi to be tempered.
so that you can do that.
Yeah. And we want it to be an automorphic form. Okay. So I am not going to discuss the proof in general, mainly because especially because I haven't gone through the details. But here is kind of how that automorphic form is chosen. You do the Plancherel measure of the Dirac measure at the identity. So write it as an integral of functionals on various representation spaces. And then given such a psi pi, for a suitable pi, you take something that looks like a matrix coefficient, except that this is not in the dual space. This is exactly this psi pi. Okay. This is the form. So matrix coefficients are nice functions, and therefore you can, and these vectors are smooth k finite and all that. So these will very easily be automorphic forms, but the non-trivial thing is that you want to take pi to be a tempered representation, and here is where Bernstein's work comes in. Bernstein shows that only tempered part of the spectrum contributes to L2, which means that this automorphic representation pi you can assume to be tempered in Bernstein sense, and which is also tempered in the sense of concave or Delorme. Okay? Yeah, sorry.
Integral over G hat. This is the Plancherel theorem for G.
No, this is the Plancherel theorem still for L2 of G of A over G of Q. No, but that will still involve G hat, right? I mean.
So what is the D mu?
No, so it is something. It is an abstract thing. We don't know anything about d mu, but of course, one has to prove some sort of non-vanishing results associated to these things. But otherwise, it's a completely abstract thing. Okay. So now we have this makes some progress into. Sorry.
G hat means G A hat.
Yeah, I should have written G A hat. Yeah.
This is a Plancherel theorem for
G A mod G Q. Yeah, I guess maybe.
That's what
Yeah. So I haven't thought about why that something has to exist. So now what is the point? So we said that if the image of the isometry were not all of L2 of G, there would be some tempered form which would be orthogonal to all the wave packets. Okay, but this is still not an automorphic form. Wave packet is a rapidly decreasing function, nice and all that, but that's not an automorphic form. It is built from an automorphic form in AP2 of G. Okay. So we want to reduce it to a pairing between AP2 of G and AP temp of G. Okay. Psi is in A temp of G. Okay. So here is how you can pair square integrable automorphic forms with tempered forms. Basically, tempered forms are always slowly increasing, these are rapidly decreasing, so you can pair. But there is one subtlety, namely, for phi in A2 of G and psi in A temp of G, you can define a pairing like this. Okay, there is also the center of G, a G comma infinity that you have to worry about. So for each element x here, you can integrate. You see, you don't want to integrate over G of A over G of Q because that has infinite measure, right? So you only want to integrate over something like G1. But G1 does not capture the whole of G, So there is that central contribution which is remaining, namely the z greater than 0 in the morning lectures. So you have to fix central elements AG, central elements x in AG, and integrate when the AG comma infinity factor is a fixed x of x. Okay. So you cannot pair them on G, but you can only get it as a function of x. But because automorphic forms, because of the considerations related to exponents that we have seen before, sorry, that's DG1. Yeah, sorry. Thank you. Okay, so it's an exponential polynomial as a function of x. So it is we denote it by P of phi psi. And similarly, if you have something in AP2 and AP10, you can still pair them, and it will be an exponential polynomial on AP. Okay. Now you start with psi instead in 8 temp of G, right? We said that you will have a tempered automorphic form with some properties if the image of the isometry was not L2 of G. Now, how can you force that tempered automorphic form to be 0? Because that theorem gave you a non-zero tempered automorphic form. So, to get a contradiction, you want to say that psi is equal to 0 using this sort of a pairing. Okay? So, for that, I need to introduce a very related notion to constant term called V constant term. Namely, if you have a tempered automorphic form, you can take its constant term with respect to any parabolic. Okay, so you can expand it like this. So an exponential function towards something which is polynomial in the AP factor. And then the point is that some of these, the temperedness means that all these exponents will be conducive to slow growth. Okay, but some of them will actually be conducive to rapid decrease. Namely, it will be some square integrality kind of thing. You throw all that away. Okay. So in the set of exponents EP of psi, so these are some elements of AG star. You take those exponents which are unitary, namely those which are conducive to slow growth but not rapid decrease. So this psi p w v constant term is actually a part of the constant term that deals with the worst of the exponents. Yeah.
So are these just the exponents which lie on the boundary of the minus positive thing?
Yeah, I think so. Okay. So, so you look at the constant term and you look at exactly the worst kind of terms in the constant term. Okay. So those form what is known as the weak constant term. And here is a fact that one can prove by some sort of easy asymptotics related arguments. You have a fixed psi element of A temp of G. If you can show that the pairing between any phi element of A, so as you vary the parabolics P, for any automorphic form phi on AP2 of G, it pairs not to 0 with the V constant term of psi around P, then your psi has to be equal to 0. Okay? So this is actually not a difficult argument at all, but I'll trip up if I try to explain it. So I will not explain it. So the point is that this pairing between A2 of G and A temp of G, you can use that. This pairing is not an inner product or anything, right? But still, you can use this product to determine when a given tempered automorphic form is 0. Namely, you will have to vary parabolics and take V constant terms with respect to all parabolics and then pair with A2 of G. Okay? So that's sort of what is going on here. Okay? So recall that assuming that isometry is not surjective, we got a tempered automorphic form that pairs to 0 with wave packets. So now, what should you do? You wanted a formula for pairing between wave packet and psi in terms of pairings of the form that we saw in the previous page. Okay? And then we need to somehow get a contradiction. And this is the main technical input that DeLong proves for that. The pairing between a wave packet and a tempered automorphic form, don't worry about this expression at all. Okay? I mean, I don't understand it. So it's some stuff which involves contributions to the V constant. Oh, this is a typo, this should have been psi. Okay? So various contribution to the V constant term of the tempered terms of the tempered automorphic form psi and your the phi. So okay, sorry. Let me repeat it. You wanted to pair a wave packet associated to P, phi, A with a tempered automorphic form psi. So you have a fixed P and you have a phi. Okay? That pairing is given by this sort of an expression. Okay, I'm not going to, so this involves differential operators, but I'm not going to explain this. You have to take the V constant term of psi with respect to the same parabolic P, and then various terms which contribute to it, and then you have to pair it with your phi. Okay, remember that phi was actually a square integrable, so this right hand side makes sense. Okay, so once you prove this theorem, what will happen? If this is true, so if this is true for every wave packets, okay, so if this is true for every P phi A, then what you know is that the pairing between all the phi and everything that contributes to the various V constant terms of psi will be 0, and by the fact mentioned in the previous page, psi itself will be 0. Yeah. Sorry. Yeah, this last fact that I had written here, whether a tempered automorphic form can be 0 or not, can be checked using pairings with various V constant terms and various square integrable automorphic forms of that. And what Delorme formula does is, it reduces to that fact by, so given P and phi, you can form wave packets like this and pair it with psi. That will give you information about the pairing between phi and the V constant term of psi. Okay. So this is the main result, that main technical input that Delorme proves. A formula for the inner product between a wave packet and a tempered automorphic form. Okay. So let me make some comments on this formula. Okay. It's not like this is the one where most work is goes in. So you see, E P phi comma A, it's a wave packet. So it's a packet made of various Eisenstein series. It's a continuous integral of Eisenstein series, and you want to pair it with psi. Okay. So obvious thing is, can you pair an individual Eisenstein series with psi? This is similar to the kind of things that we saw at the beginning of the talk. But this doesn't make sense because psi is only tempered, so this pairing is not going to converge. Okay. So one obvious thing might be to truncate the Eisenstein series, but that's not what Delorme does. Instead, Delorme calculates the pairing not on all of G of A over G of Q, but he computes this on a subset that depends on a parameter T. Okay. So CTG is a large subset of. So I am assuming that AG equal to 1 for simplicity, or we can even assume that G is semi-simple for simplicity. So CT is a large subset of G1 depending on the parameter T. Okay. So instead of getting a formula for pairing between wave packet and tempered automorphic form, it's a formula for a pairing between Eisenstein series and an automorphic form, except that you are only integrating over larger and larger subsets of G of A over G of Q, which are of finite volume. Okay. So this is kind of like the truncation that Arthur uses for local trace formula. Instead of truncating by subtracting constant terms from depending on cutoff, what you are doing is you are just choosing to integrate on some finite volume region instead. Okay. So conceptually this might look simpler, but it can okay, so it can lead to other difficulties. Lapid's ICM talk indicates a slight variation where instead of integrating over a large subset, he is actually integrating on G, but he is actually using truncation. Okay, so I don't want to discuss more details. Of course, I don't think Lapid's approach is. I don't know if Lapid's approach is actually written out in detail anywhere. But to do this sort of thing, you need to know how truncated Eisenstein series look like, and there is a formula of Lapid and Ouellette for it. But anyway, that's just too specialized. Okay, so I've kind of a waving hands is not enough to describe what I have done so far. But now I'll kind of make some very informal comment on the work of Bernstein and Lapid about how you meromorphically continue Eisenstein series. So crudely, this is what they do. Crudely, they show that Eisenstein series can be characterized using a system of equations varying automorphically in a parameter S. So this should be ignored, okay? It should contain some additional conditions. Yeah. So the Bernstein's principle of meromorphic continuation says that under additional conditions, this system has a unique family of solutions which is meromorphic in S. Okay? So once you can get a characterization for Eisenstein series, and you know that the solution solution is unique in some region of S, and if you know that that solution has some additional nice properties, then there is a unique meromorphic family of solutions, and that will force Eisenstein series to have a meromorphic continuation. Okay. So of course yeah. So let me write a little bit more on that. So what does equation mean? Like when we start studying linear algebra, we see equations as kernels or fibers of linear transformations between vector spaces. Here you have to consider locally convex Hausdorff topological vector spaces, and you are interested in linear equations in a given vector space F, and these equations are given by linear maps to various other vector spaces Fi. Okay, and everything should be. So we want to study meromorphic continuation. So it's like you have a system of equations. The coefficients of the system of equations are going to be holomorphic functions in a parameter S. Okay. So you have continuous linear maps Ai of S from F to varying Fi, and you have elements Ui of S, element of Fi, and both of them are required to vary holomorphically in a complex variable S. So it's like you have systems of equations whose coefficients are varying holomorphically. Okay, so S can be in C, it can be in a finite dimensional vector space or a complex manifold, and equations are of this form. Okay, so this is what linear equations mean for us, and then there should be additional conditions to ensure that this has a unique meromorphic family of solutions. Okay, so these are the additional conditions. For S in some open set, there should be a unique solution. Okay, P of S. And there should be additionally a condition called local finiteness, namely, the solutions locally should be contained in the image of a map from a finite dimensional vector space. Okay, so the fact that you have to have a finite dimensional vector space, so it has to be basically some sort of a finite problem in some sense, at least locally. Okay, so you should have a fixed finite dimensional vector space L independent of S, and then there should be a holomorphic family of operators from L to F, such that solution should be contained in it. Okay, all this should happen locally. So this is what meromorphic Bernstein's principle roughly says. Under these conditions, there is a good system of meromorphic solutions to it. Okay, it's a clever application of Cramer's rule. In finite dimensional case, we know that if you have a holomorphic system of equations with a unique solution, then some determinant is invertible, and it continues to be invertible in the neighborhood, and the inverse is actually a meromorphic function. Okay, that has to be very kind of cleverly applied to show that the finite situation can be locally reduced to the infinite situation can be locally reduced to finite situations at various points. But yeah. Locally in S. Sorry, locally in S. Yeah. So okay, let me not try to explain, but it's not like one can just drop the word Cramer's rule and derive this, but there is some cleverness going in. And how do you ensure that your system of equations is locally finite? So one way is that there should be a difference between they should be given by a difference between two operators, one of which is compact, namely typically you show compactness using Hilbert's witness, and the other should be a special kind of operator called it could be a kind of operator called strict embedding, namely it should be a homeomorphism onto a closed subspace of the target. Okay. So this is basically what the principle of meromorphic continuation says. So let me make some informal comments on how Bernstein and Lapid use this strategy in the case of the upper half plane. Okay. So this is the usual Eisenstein series on the upper half plane. Okay. So this is a variant of whatever Selberg had done. So there are two things you need to do here. One is a uniqueness thing. You need to characterize E of Z as uniquely on real part of S greater than 0. Yesterday Sanya had asked me, how can you characterize, is there a way to characterize Eisenstein series uniquely? So this is one thing that they do. Then one needs to add more equations to ensure that locally solutions to the system of equations has to be finite. Okay. Okay, so let me give some idea of one. Okay, I am going to skip two totally. Okay, how are you going to get equations that can characterize the Eisenstein series uniquely? Okay, So let psi be E of Zs. We want to get enough conditions on psi to characterize psi as E of Zs uniquely. Okay? For real part of s greater than half. So we know the constant term of psi, right? So here I have written psi b for the constant term of psi. It is y raised to s plus half plus something times y raised to minus s plus half. Okay? So this y raised to minus s plus half is a very nice kind of function. If you translate it by a function a, what do you get? A raised to minus s plus half comes out. And then you multiply it with a raised to minus half to destroy that minus half part. So it is an eigenfunction for Ta with eigenvalue a raised to minus s. Okay? So constant term minus y raised to s plus half is an eigenfunction for this translation. And the second condition is that it's orthogonal to all the cusp forms. Okay? So let me give some idea of why this characterizes the Eisenstein series uniquely. Okay? So suppose psi satisfies this, I want to show that. So David also explains this in his ICM talk, not ICM talk. This is a or IHES talk maybe. So yeah, I don't know which talk it is. So consider psi minus E of z comma s. Okay? If psi satisfies these conditions, you want to show that psi is equal to 0. Okay? How do you show that? Look at the constant term of psi minus E of zs. Okay? What can you say about the constant term? The dominant part of y raised to s plus half is the same for both psi and E of cs. So this is equal to something times y raised to minus s plus half. Right? And when real part of s is greater than half, this is going to be less than 0. Right? So the point is, the constant term of the difference goes to 0 as y goes to infinity. Okay? If the constant term of the difference goes to 0 as y goes to infinity, psi minus E of zs goes to 0 as y goes to infinity. Because as y goes to infinity, constant term captures the asymptotic of the automorphic form, right? And here is the thing, if an automorphic form goes to 0 as y goes to infinity, what can you say about it? Which means psi minus E of z comma s is bounded, right? So psi minus E of z comma s is bounded. What does that mean? This guy is bounded, the constant term is bounded. If your automorphic form is bounded, its constant term is also bounded. But what is a constant term? It's a multiple of y raised to minus s plus half. It cannot be bounded as s goes to 0. It's of course bounded as s goes to infinity, that is what we used. But then we have gone to the automorphic form and come back with the consequence that it is bounded as s goes to 0. Okay? And that implies that the constant term is 0. If its constant term is 0, what does it mean? It means it's a cusp form. But the second condition says that it's orthogonal to all the cusp forms. Okay? So that is how you uniquely characterize the Eisenstein series for real part of s greater than half. Okay? And then I'll skip the local finiteness. There are more equations that you need to add. So I don't think I'll get time to discuss the general case. So again, but what you need to do is that just like with upper half plane modulo gamma, for lambda in some cone, you have to characterize the Eisenstein series using exponents. Okay? And the characterization will involve two conditions. Namely, one will have to use a notion called leading cuspidal exponents. Namely, you take exponents along you take a constant term along a parabolic, project onto the cuspidal part, and then look at the exponents. Okay? And you are not looking for all the exponents, but you are only looking for those exponents with the property that with a row shift it belongs to the positive Y chamber. Which means, in the earlier case, s plus half and minus s plus half, only s plus half is a leading exponent, minus s plus half is not leading. Okay? But that s plus half being the only leading exponent was enough to characterize the Eisenstein series. Okay? So basically, so this is a generalization of the earlier thing. You can characterize automorphic forms by matching leading cuspidal exponents. Okay, let me not elaborate much on that. And one non-trivial and interesting theorem that they prove as part of it is that any non-zero automorphic form has a non-zero leading cuspidal exponent. Okay, so it's not like any automorphic form has an cuspidal exponent that lies in the Weil chamber, but it has a cuspidal exponent that is at least sufficiently close to the Weil chamber. Okay.
Automorphic form which is not a cusp form.
No, so if it is a cusp form, you can think of it as its own cuspidal exponent, right?
Ah.
Yeah.
So you're saying any automorphic form has a leading cuspidal exponent belonging to minus rho plus.
Yeah, leading means it has to belong to rho p. Minus rho p plus positive Y chamber. Yeah. Yeah, it almost reminds me of how in the BRD case, the constant term of the Steinberg, the exponents of the Steinberg are not positive, but it is kind of close enough to the Weil chamber. Okay, so more equations are needed for local finiteness, and not just that, you are only on uniform moderate growth functions. Okay, that's the topological vector space under consideration. So you also need equations to get from there to the space of automorphic forms, okay, and uses versions of Harishchandra's results. Okay, so let me just list out a bunch of related results that follow. Once you have meromorphic continuation of Eisenstein series, you can also deduce the meromorphic continuation of intertwining operators because they occur in constant terms of Eisenstein series. Okay, so you have to think of ways to isolate intertwining operators, the contribution of a Weil element within an Eisenstein series. Okay, within a constant term of an Eisenstein series. So you can also get meromorphic continuation of intertwining operators. Secondly, this machinery also allows you to get functional equation for the Eisenstein series. And how do you do this? One uses the characterization of automorphic forms using leading cuspidal exponents. So the point, what is this? The thing is, you can relate the exponents of the Eisenstein series to exponents of the inducing datum, but the leading cuspidal exponents of the inducing datum, and they can be compared across intertwining operators because intertwining operators are intertwining. So you have to worry about the leading part, and then so because they are characterized, you can show that both of these satisfy the same characterization. Okay. Then you can show the multiplicativity of intertwining operators. That's by using the functional equation and the fact that for generic lambda, sending field to your field as injective, and one can also recover the result that singularities of Eisenstein series as well as intertwining operators on root hyperplanes. So this is almost obvious if you have an elementary symmetry. There, the intertwining operator only depends on this sort of thing by definition, and the general case follows from multiplicativity. And then the case of Eisenstein series can be deduced once you have for intertwining operators. Yeah, so that's all I wanted to say. Sorry, I mean, I'm talking about things that I don't really know, and yeah.